mu nu times I k dot x with k square equal to 0. And I should just add that because these are linearized equations, even any solution, okay, an arbitrary superposition of solutions is also a solution. Okay, so you can take, for example, this integrated over k with some arbitrary weight factor. Okay, that will also be a solution as long as this integral only runs over values of k for which k square is 0. Okay, so we then impose a set of gauge conditions. And in terms of E mu nu, the gauge condition took the form that E mu nu minus half k nu E lambda lambda equal to 0. And then we saw that there is a gauge transformation which is E mu nu goes to E mu nu plus I. Okay, where f nu is arbitrary constants. And the point is that this quantity here automatically satisfies the gauge condition as long as k square is 0. And that is the reason why even after gauge fixing we can still use this to shift our E mu. Okay, because this doesn't change the gauge condition. So to begin with, these had 10 independent constants E mu nu. There are 4 gauge conditions that removes 4 of the independent constants, and then there are 4 gauge transformations. So by adjusting the f's, we can try to get 4 more linear combinations of E mu nu to 0. So effectively, we see that we have 10 minus 4 minus 4, that's 2 independent constants that's left over. Okay, after we have imposed the gauge condition and after we have used up the gauge freedom. So what we will do today is to make a convenient choice of these constants. So for this we will choose a specific k, k0, k1, k2, k3 as k 0, 0 minus k. Where k is some constant, which basically means that we are taking this momentum vector k to be along the third direction. Sorry, k0, 0. Let's take it last. We are taking the momentum vector to be along the third direction, and then this automatically satisfies, of course, k square is equal to 0. Okay? Because eta mu nu k mu k nu is k square minus k square. That's it. So let's see what, with this choice of k, what condition do we get on the E mu nus by solving this equation. So we will get clearly k0 is 0 nu plus k3 is 3 nu. Okay? Those are only 2 independent constants. So we get k times E0 nu plus E3 nu minus half k nu. And now E lambda lambda I'll write out explicitly. That's minus E00 plus E11 plus E22 plus E3. Is this okay? So this should be 0. And now we take mu equal to 0. This we have to write all 4 equations explicitly. So mu equal to 0 will give you k times E00 plus E30 minus half. K0 is minus k. Okay, because it's lower index, so half times minus k minus E00 mu equal to 3 will give you k times E03 plus E3 minus half times k, and then we will do something. Mu equal to 1 will give you k times E01 plus E1 equal to 0. Then because k1 is 0 and E equal to 2, will similarly give you k times E02 plus E32. Is this okay? Now it's easy to see that if we subtract second equation from the first equation, okay, so k we can drop, of course, okay, because k is just an overall constant, so which you can drop. If you subtract the second equation from the third equation, from the first equation, these two terms cancel. Right? The E30 and E03 are the same, it's a symmetric. Right? So you get E00 minus E33. So V equal to 0 minus the V equal to 3 equation gives you E00 minus E33 and then plus, essentially this is half k, this is minus half k, so it's just doubles, plus minus E00 plus E11 plus E22 plus E33 equal to 0. So you see that these cancels, so you get E11 plus E22. Once you have gotten E11 plus E22 equal to 0, we can substitute it here. Okay, so E11 plus E22 is equal to 0, and that basically boils down to, so now substitute into V equal to 0 equation. So what it gives is E00 plus E30 minus plus half minus E00 plus E33 equal to 0, or E03 plus half of E00 plus E33 equal to 0. So these two equations are essentially consequences of the nu equal to 0 and nu equal to 3. And then you also have the other two equations, E01 plus E31 equal to 0 and E02 plus E32. Is this clear? So what I did is that I just subtracted this one from this one to get one equation, that's E11 plus E22 equal to 0. Now I substitute here to get this equation. Now this equation doesn't have to be used anymore, okay, because this equation has already been used up in combination of this. So once you have these two equations, you have automatically satisfied these two equations. Okay. So you still have to use these two equations. Okay. So these are the four equations that we get from the gauge fixing condition. And now we have to try to see how we can simplify things by using this. So this I will not go into very much details, but let me just indicate how things work. So let's say E01. E01 goes to E01 plus I times K0 F1, okay, that's minus K F1 plus K1 F0, K1 Z0, okay. So which means by choosing F1, we can make this vanish. All you have to do is that if we start with some E01, we have to take F1 is equal to E01 over I times K. Okay. Now at this stage, you need not worry about the fact that it becomes complex, because these E's are not real anyway. Okay, because e to the I K dot x is not real. Okay, at the end, of course, when you take appropriate linear combination, you have to make sure that you take the real linear combination. Okay. So at this stage, you can see that by adjusting F1, we can make E01 vanish. So F1 makes E01 equal to 0. Similarly, F2 will make E02 equal to 0. The same thing. Just take E02 goes to E02 plus I K0 F2 plus K2 F0, but K2 is 0.
For the E's, they will be complex, that is
3 maybe.
Here because the solutions it had e to the ik.
Yes.
But if one was related to a coordinate transformation, then
yes, but there also the zeta was f times e to the ik dot x, right? Zeta mu was f mu e to the ik dot x. So that's also complex.
It also will happen when I take 3 instead of 0.
No, for 3, the K3 is non-zero. So formula is a little different. You see, K is this, right?
No, not E03. I am saying E31, E32.
yeah.
Yes, once you have gotten this, right, then you can see here that this condition automatically tells us E31 and E32 should be 0. Okay, because you cannot, of course, use F1 twice. Right?
Yes, absolutely.
You can use F1 only once and then you see what you get. Now, of course, you don't have to choose F1 this way or F2 this way, but it's just that this choice makes things a little more convenient, right? Because you are trying to make as many things 0 as possible. Okay, let's now check what you can do with E03. So E03 goes to E03 plus I. This is K0 F3, okay, so minus K F3 plus K3 F0 plus K F0. What about E00? E00 goes to E00 plus I K0 F0, so minus F0, and then again K0 F0 minus F0.
K.
into K.
Overall.
This time. So we see that by adjusting F0, we can make E00 vanish. Okay? And then by adjusting F3, we can make E03 vanish. Okay? So adjust F0 to get E00 equal to 0 and adjust F3 to make E03. Now you can combine with this. So you see that from this, because we have made E01 equal to 0, this now tells us that E31 is equal to 0. And this tells us E32 equal to 0. Now E03 has been made 0 anyway, E00 has been made 0 anyway. So this tells us that E33 is 0. So what you are left with are the non-zero components and E12 and E11, which is equal to minus E2 by this relation. And you would notice I erased it. Let me write it again. So E mu nu goes to E mu nu plus I K mu F nu plus K mu F nu. Because K1 and K2 vanish, it's clear that there is no way you can use the F's to change the values of E11, E22 and E12. Right? Because you are either get a factor of K1 or a factor of K2, okay, which makes this vanish. So E11, E22 and E12 are really gauge invariant, they cannot be changed. And we have this relation E11 equal to minus E2. So these then gives you the non-vanishing components of the polarization tensor or the metric. Okay, in this specific gauge. Is this clear?
So once you have fixed this gauge,
Yes.
is there any way to check that for these two non-zero components it will be a unique solution? There is no other gauge freedom. Is there any way to check?
Yeah, because you have already fixed all the gauge freedom, right? Because you used F0, F1, F2 and F3. Right? So in that sense there is nothing else left that can change this. Because to begin with, the gauge freedom involved an arbitrary function, zeta mu. Right? But then we say that we can restrict, we have to restrict zeta mu to be of the form f mu into the ik dot x with k square equal to 0, because we want to keep the form of the metric, right? E mu nu e to the ik dot x was the solution. You don't want to change that form. Right? So that already ruled out an infinite set of possible gauge transformations, right? But in general, you could take this to be zeta mu to the ik dot x with an arbitrary k. Okay? So you already ruled out infinite set of gauge transformations. There is still some gauge parameters left, and now we use those gauge parameters, all of those, to fix this gauge. So there is nothing else really left over now.
This is unique. So this is unique. No?
This is
E12 and E11 equal to minus E22. This is unique.
yeah, this is unique in this gauge, right? Because we have chosen a specific gauge,
Yes.
right? Yes. So in this gauge, it's unique. Then you cannot remove anything else from here. Is this okay?
When we discussed yesterday, we were talking about like two independent components.
Yes.
And we can see that here two independent components.
Exactly. So U12 is one independent component and U11 is another independent component. Okay. So this is of course the general basis, right? That you just take. So you can take the two arbitrary constants U11 and E22. That will give one possible solution or one possible configuration of gravitational waves. Okay. The full configuration, let me write it. H11 will be E11 into ik dot x plus U11 star to be minus ik dot x. Right? If you want things to be real, similarly H12 will be E12 into ik dot x plus E12 star to be minus ik dot x. And similarly, and H22 of course is just minus H11 because of this relation.
Now our case would be the special formula
Yeah, case would always satisfy k square equal to 0.
with k00 minus k neither.
Yes, that's right. Yes, that is true. If you want to change, rotate your k, yeah, so you have to change this basis also. Okay?
This is a wave moving in the z direction.
Yeah, this is a wave moving in the z direction.
So sir,
Yes.
here E12, E11 and E22 you told that it's gauge invariant now.
Yes.
So they will be
Well, it's gauge invariant in this specific case. That is, this is invariant under residual gauge transformation. We have already fixed a gauge,
yeah.
right? Then there is a residual gauge symmetry, and these are invariant under the residual gauge transformation.
Yeah, so like as he asked that first you have a k, assuming that your k is not in your x3 direction.
Yes.
Then when you rotate that k, at that time your E12, E11 and E22 will change, right?
Yes, exactly.
At that time they will change, but now when you do a change in your k, then it won't.
No, we are not changing k,
Uh-huh.
right? Because we have fixed our k, right? We determined this by fixing our k, right? Because it was important that to show that it's gauge invariant, we have to use the fact that k1 and k2 are 0. Right? If you take a different direction, then of course k1 and k2 are not 0. Right? Then this will not be gauge invariant. This will not be invariant even under residual gauge transformation.
There will be some other.
Yeah, there will be some other combination which will be invariant. Okay, so as I said, this is the independent basis, but like in electromagnetism, it's often convenient to use a different basis which describes circularly polarized waves. So what are circularly polarized waves? Okay, circularly polarized waves are those which behave nicely under a rotation. Okay. Now the rotation that is of relevance here is a rotation about the z-axis. Because of course if you rotate along any arbitrary axis, the momentum vector itself will change. Right? So then this analysis that we have done doesn't work anymore. Okay? But keeping the momentum vectors fixed, okay, we can still rotate in the 1-2 plane, right? Which means in the around the z-axis. Okay? And circularly polarized waves, okay, by definition are the ones, okay, which are eigenstates of such rotation, okay, which changes by an overall phase under such a rotation. Okay, so instead of mixing with each other, this is a two-dimensional vector, right? Because this two-dimensional vector space, okay, labeled by E11, E12, and E22, of course, is the same as minus E11. In this two-dimensional vector space, we can choose a basis in which the individual basis vectors are eigenstates of the rotation operator. Okay, rotation about the z-axis. Okay. So the question is, how do you determine, okay, which particular linear combinations have that property? So I will not do the full analysis, but I will just give some sketches. So what is rotation matrix in the 1-2 plane? So this is 1 0 0. So this is our 0, this is 1, this is 2, this is 3. Okay, so we rotate in the 1, 2 plane. Now rotation of course is a special case of general coordinate transformation. Okay, but it has a feature that under this transformation, this particular general coordinate transformation, eta mu nu doesn't change. Okay? That's what is special about Lorentz group. Okay? The eta mu nu as a metric remains unchanged even if you perform a general coordinate transformation under the Lorentz group. Okay, the rotation is some specific part of that. So if you want to know how the metric transforms, general metric, not eta mu nu, how a general metric transforms on the rotational group, we can use the same formula, that g prime mu nu of x prime is 0 sigma of x times del prime mu x rho del prime mu x sigma, where x prime and x are related by the rotation matrix. X prime mu is r mu x. So if we now use g mu nu of x as eta mu nu plus h mu nu of x and g prime mu nu of x prime as eta mu nu plus h prime mu nu of x prime, and use the fact that small h approximation, but this is not even necessary in this case, we will get h prime mu nu of x prime as h mu nu of x. It's not necessary small x approximation. So this will give you basically R transpose comes. Okay, so H prime as a matrix is essentially R transpose H of x R. This is a matrix. Think of this as a matrix. It's clear, just substitute. We have the expression here. So just substitute h prime mu nu of x prime as this, and this is what you will get. Okay, so here del prime mu of x rho, so you have to derive, take the derivative of x rho with respect to x prime mu. So you have to invert this. So this implies also that x mu is R transpose mu x prime. Right? Because R transpose is similar R inverse. Okay, so using that we can verify this. Okay. Now the x dependence of h comes from the e to the I k dot x factor. Okay, and because you have taken k to be along the 0 and 3 direction, okay, it doesn't involve x1 and x2. Right? E to the I k dot x is invariant. So x dependence, so h prime mu nu of x prime is the same as h prime mu nu of x, because k dot x is equal to k dot x prime for k equal to k 0 0. Right? Because if only the 0 and 3 components are non-zero, then we can easily see from this transformation law that x prime 0 is x0, x prime 3 is x prime 0 is x0 and x prime 3 is x3. Okay, so k dot x prime, k dot x and k dot x prime are the same. So the only effect of this rotation of this transformation is on the e mu nu part. Okay, the fact that here you have x prime, here you have x, makes no difference. Is that clear? So you can translate this to e prime mu nu is equal to r transpose, e prime is equal to r transpose mu r. Okay, again you think of E as a matrix. So E is a matrix. So the element part of this equation is in the 1, 2 plane. So I can write E prime 1, 1, E prime 2, 2, E prime 1, 2.
So both 1 2 or 2 1?
1, 2 and 2, 1 are the same.
Symmetry.
And it is symmetric.
You have just written the like 1 2 part of R, right?
Yes, because upon the R, no, yeah. So this is a 1, 2 part of R. So let me. So this is called R tilde. So R tilde is basically cos theta sin theta minus sin theta. Okay, you think of this as a 2 by 2 matrix rather than 4 by 4 matrix. So because that's an only non-trivial part that's acting. So using this, okay, we can expand it out and we can calculate explicitly what this prime quantity is in terms of R prime parts.
Sir, I couldn't understand this state. What is that taking actually? X prime is equal to H prime X. Where is that coming?
Yeah, because the point is that H prime, so what is H? H mu nu was E mu nu of e to the I k dot x, right? Okay. And the point is that because k has components only along the 0 and 3 direction, k dot x is the same as k dot x prime. Is that clear? Because x prime, so k dot x is k times x0 minus x0 plus x3 or x0 minus
The
x3.
transformation of H is equivalent to the transformations in E prime.
Exactly. Yeah. So the point is this part doesn't change at all. Okay? Because since you are rotating in the 1, 2 plane and since the momentum is in the 0, 3 direction, 0 and 3 direction, okay, the k0 and so this, if you write it explicitly, this is like e to the I k times x0 minus x3. Okay. And x0 and x3 don't change. X prime 0 and x0 are the same, x3 and x prime 3 are the same. Right? So because of this argument, the fact that the argument x has changed to x prime, that's irrelevant. Okay? Not in general, but as far as the x dependence of h is concerned.
So only the transformation is between E's.
Yeah, exactly. So the only the transformation is between the e's and that's what I have written. And now I'll leave it as an exercise to check
dot x that remains unchanged, that is anyway means just a property of the rotation.
Exactly. K dot x of course remains unchanged, right? But k dot x and k prime, so but k would change to k prime. In this case, k prime is the same as k. So there may be sign error. This you should check. Okay, this follows straightforwardly from here. So let me write it in some time. The corrective case will be something like this. So this means that if U11 is equal to I U12, then E mu and if U11 is equal to minus I U12, then I mu. So basically what we are saying is that if this vanishes, which is U11 equal to I U12 or U11 equal to I, okay, the only non-vanishing component is this one, and that picks up a phasor between 2I theta. On the other hand, if this one vanishes, if U11 plus I U12 vanishes, then the only non-vanishing component is this one. Okay, and it picks up a phasor between minus 2I theta. So these are the circularly polarized waves. That you have to choose E. So you see that E11 and E12 are of course always related. E11 and E22 are always related. E22 is minus E11. Okay. What this is telling us is a way to choose E12. Okay. If you choose E12 to be minus IE11, then the polarization tensor picks up a phasor between 2I theta under this rotation. If E12 is I times E11, that is this case, then the polarization tensor picks up the phasor to be minus 2I theta.
Is it just rotation in opposite direction?
It is a rotation in opposite direction. Exactly. The rotation is in the same direction, okay, but the phase that it picks up is opposite. Okay, this is exactly what happens for circularly polarized waves. Right? For in electromagnetic wave, right, you have the x polarization in the transverse planes, right? The x direction and y direction. Okay? If you take x plus iy, right, that picks up a phasor between the I theta. X minus iy picks up a phasor between the minus I theta. Okay? So this is the generalization of the circularly polarized wave. Okay? But you see the difference that instead of putting up into the plus minus I theta, you pick up into the plus minus 2I theta. And this has to do with the fact that this H mu nu was a rank 2 tensor rather than a rank 1 tensor.
So, what is the transformation condition for K? Like in general, if you want to see, if I do a transformation,
Yes.
then what is the condition of?
Well, the point we have given the transformation on x, right? X is a coordinate. Transformation on k is up to you, right? That you start with some function e to the I k dot x, okay? And often it is useful to think of k prime as such that k dot x is equal to k prime dot x prime. See, k is just a label here, right? So in that sense, you can assign a transformation or you may not assign a transformation, but it's convenient to assign a transformation law to k so that k dot x and k prime dot x prime are the same.
So x is a vector here, so k also transform in the same way. K is a vector.
Well, k dot x, right? What I have written is just a symbol. It's the symbol which is eta mu nu k mu x nu. Or the other way. Eta mu nu K mu x. Okay, because K is just a set of parameters which are leveling the plane wave.
It's not a vector of the same space.
Yeah, it's not a vector in the same space, and the point is, it's just, you just think of it as a level, right, of the plane wave. It's convenient to assign a transformation not to that level, but you don't have to do that.
So sir, this means that if assume I assign it to vary like a vector,
Yes.
then I can do this analysis independent of the choice of, like, since my k dot x will remain invariant now in transformation.
Well, see, yeah, so the point is, that's more complicated because the e's also have to be changed. Right? It's not just k dot x. If you let k transform, right? Suppose you use a rotation which doesn't preserve the third direction, right? Which takes the third direction to something else. Okay? Then of course, yes, k dot x you can declare that this is equal to k prime dot x prime, but the e's will also change.
Yeah, e will change to e prime.
Exactly. Right? So to classify how it transforms a rotation group, okay, it's always useful to only identify that part of the rotation group which leaves the momentum vector unchanged. Okay, and that in this case is the rotation in the 1, 2 plane. Okay. If it is a massive particle, okay, then typically you can go to the rest frame, and then you have the full rotation group. Okay, and you can classify the transformation under the full rotation group. For massless particle, right, which always moves at the speed of light, this is the best you can do. Right, and that's what we have done here.
Sir, here we told the two theta in the same direction of rotation.
Same direction of rotation, yes,
2 theta and minus 2 theta
are opposite directions. So these are left and right circularly polarized waves. Right? Because rotation is in the same direction. Rotation matrix I have chosen once and for all. Okay? But under this rotation matrix, the question is what phase does it pick up?
Then one is rotated in this side, then the opposite direction.
Yeah, rotation is in the same direction, but it transforms in the opposite way. Right? I mean, okay, maybe it's just a nomenclature. I mean, you think of a rotation in the xy plane, it is a fixed rotation. Right? But x plus iy and x minus iy pick up opposite phases. Right? Because x plus iy is r into the I phi. Right? If phi is the azimuthal angle, x minus iy is r into the minus iy. Right? So under phi goes to phi plus theta. Right? That plus theta is always plus theta. But the phase that it picks up is into the I theta in one case and into the minus I theta in the other case. Right? So that's all you are saying. Yeah.
How is the count of the independent components is consistent? Like these last two lines that you have written, if E11 equal to E12, like you have to have two independent components still, right?
These are the two.
No, because once you have said U11 equal to minus U12, right? You are choosing the one particular basis in this two-dimensional vector space. See, the two-dimensional vector space was labeled by E11 and E12. E22 is fixed anyway, right? Now we are putting a condition on U11 and U12. Right? That's like picking one particular basis vector in this two-dimensional space. Right? That basis vector has a property that it picks up a phase of equal to 2 I theta under rotation about the z axis. The other basis vector is this one. Okay. So in other words, I mean, you can define E hat 1 as E11 plus IE12 and E hat 2 as E11 minus IE1. Okay. Well, instead of writing, think of E11 and E12 as independent variables, you can also say these are the independent vectors. And now you are saying that if E hat 2 is 0, then E hat 1, then you are basically choosing a polarization tensor along the E hat 1 direction. Okay. That picks up a phase of equal to 2 I theta under rotation. And then if this is 0, then this is a vector you are choosing, and that picks up a phase in the opposite direction. Is that?
So, in even if you are working on very particular gauge, for instance, but when we calculate something observable, that has to be gauge invariant.
Exactly, yes.
So here up till now, have you seen anything which can be gauge invariant?
Well, this is gauge, this notion, the notion of left and right circularly polarized gravity waves, this is gauge independent. Right? Sometimes what may happen is that if you make a gauge transformation, if you make this rotation for example, if you choose a arbitrary gauge, right, it may take you out of the gauge condition. Okay? Then you have to make a gauge transformation to bring it back into the original gauge. And then you again find that it picks up these fields.
So anything observable has to be independent of E1 and E11 and E12. Because, no, anything that we want to see that it is gauge invariant, we calculate something observable which we want to see that it is gauge invariant.
Yes.
It will have to be independent of E1.
No, it will not be independent of E1 and E12. Because it's a question of what you want to calculate. Suppose you want to calculate how this affects an experimental setup. That's a gauge invariant question. Right? So this particular polarization affects, suppose there are a gravity wave coming with this polarization, right? You have to equal this. That affects the experimental setup in a certain way. Now in a given different gauge, it may not look like this.
The effect must be same.
But the effect will be the same. Right? So here you have fixed the gauge, you have done the calculation, now we can study its effect on the system. That effect will be the same, irrespective of which gauge you use to describe it. Is that okay?
So why we are getting the factor of 2 there?
Because as I said, it's a tensor, right? I mean, gravity wave describes a spin 2 particle rather than a spin 1 particle, right? The photon describes a spin 1 particle, not electromagnetic wave. This describes a spin 2 particle. That's why you are getting a factor of 2. Okay? Under rotation, you pick up twice the amount of phase, the square of the amount of phase that you would have picked up if it was a electromagnetic wave.
We are rotating in the space of E1, E11 and E12 only.
No, we are rotating in the space of 1, 2. Okay? Because this rotation matrix
Yes.
is in the 1, 2 plane, right? The physical rotation. That affect that acts on this, okay, by a transformation like this, and when you work it out, you find that this combination pixel phasor between the two I theta. That is just a direct consequence of that. If it is a vector, for example, then there will be no 1 R acting on a vector, right? That's what gives rise to e to the I theta, okay, on xy. Here, because it's a tensor, R is acting from both sides, right? And that's what is responsible for the fact that you get e to the 2 I theta rather than 2 I theta. Okay, now let us, for time being, go back to the full Einstein's equation, and this will allow us to define what we will call the energy density of the gravitational wave. But let's forget about gravity wave for now and go back to the full Einstein's equation. So this, of course, has the form of R du nu minus half R g nu as minus 8 pi u times T. Okay, that is the usual energy density of coming from all the sources. Now, I will define R1 mu nu as the linearized part of R mu nu. And explicitly we had worked this out. So this is given by del rho h mu minus del lambda h mu minus okay, so this is by definition what is R1.
Here we are not putting any condition on H to be small or something.
Not yet, yeah. So right now this is the definition. So we define R tilde mu nu as R mu nu minus R1 mu nu. So this is by construction quadratic and higher order in H. Okay, because you have taken out the linear piece in R1 mu nu, so this difference is automatically quadratic and higher order in H. We also define R1, right, R1 as eta mu nu times R1 mu nu. So this again you can work out what this is. So all you have to do is to just multiply by eta mu nu. So you see that this first term and the second term are the same, right? Because this gives you box of h lambda lambda, this also gives you box of h lambda lambda. So this is 2 del rho of h lambda lambda minus 2, again these two terms will be the same. Okay, once you contract, sorry, these two terms will be the same once you contract mu with mu. So that's basically del rho del sigma HFC. Is this okay? And then we define R1 tilde is R minus R1, sorry, R tilde as R minus R1. Again, this is quadratic and higher order in H. So what you are going to do is to substitute this in the Einstein situation and keep the terms involving R1 mu nu and R1 and eta mu nu on the left hand side and put everything else on the right hand side. We will get R1 mu nu minus half R1 eta mu nu is equal to minus 8 pi g e mu minus r tilde mu minus half r tilde eta mu minus half h mu. Okay, so what did you do? So r mu nu I wrote as r1 mu nu plus r tilde mu nu. R mu nu I wrote as r tilde mu nu plus r1 mu nu. Then r tilde has come on the right hand side. That's why it's minus r tilde mu nu. This term r, first of all g mu nu I split into eta mu nu plus h mu nu. Half, and then finally after I have done that, here you are left with r1 times, sorry, r times eta mu nu. R I now split as r1 plus r tilde, and the r tilde term we have again brought on the other side.
So here is h mu is anything.
H mu is
Arbitrarily higher.
at this stage, yes. Okay, we have not made any assumption about h mu being small.
So when you are taking r tilde times eta mu,
Yes.
you are making
No.
g mu is equal to eta mu plus h mu.
Yes, g mu is equal to eta mu plus h mu, right?
Oh, r
So half our h mu is already here, is here. Okay, this is exact. This is just a rearrangement of lines and such. The important point is that each term here is, when you expand in parts of h mu has quadratic and higher order terms in h mu. Okay? This one by construction is quadratic in h mu and higher order. This by construction is quadratic and higher order. This one, okay, there is an explicit factor of h mu, and R of course contains linear and higher terms in h mu. Okay? So this is also quadratic and higher order. We now declare this to be 8 pi g times Tg. So this is the definition of Tg. And this we identify, okay, it's just a definition, but we call this the energy density of the gravitational law. Okay, or energy density in the gravitational field. Is this clear? So then I can write the right hand side as minus 8 pi g times T mu plus Ag.
So why have we ignored the R1 times H term?
Yes.
We have ignored that, but why have we ignored that? Because
No, we have not ignored that.
where is
Because RH means R contains R1 plus R1 tilde.
okay,
Right?
okay.
Yeah, so that's not ignored. Because this is the full R. For practical calculation, of course, I mean we only keep the quadratic term, right? Because typically in a kind of gravitational field that we take, the effect of cubic and higher order terms is extremely small. Even the effect of the quadratic term is extremely small. Nevertheless, it's often enough. I mean, for all practical purposes, it's enough to just keep up the quadratic term. But in general, this contains terms of arbitrary high order. Now let me give a justification of why we try to call this the energy density of the gravitational wave or the energy density of the gravitational field. So for that we have to look at the left hand side. So the left hand side is R1 mu nu minus half R1 theta nu. So this now I am going to expand out. So R1 mu nu was del rho H mu nu minus del mu del lambda H lambda nu. So I can just write this lambda because the contractor index minus del mu H lambda nu plus del H lambda lambda del mu del mu. Okay, this is the R1 mu nu, and now you have to subtract from this minus half, so minus half eta mu nu. R1 contains two pieces, so that had a factor of 2 if you recall, because once you contract this theta mu nu, the first and the last term they have the same result, and these two terms have the same result. So this is del rho H lambda lambda minus del rho del sigma H epsilon. Is this okay? Now it's a simple exercise to check
This form gives this.
yes. If we just take this and just contract to del mu, right, you will see the terms just cancel pairwise and it gives you 0. Okay, it is just a direct consequence of this. Is this statement clear?
It is expected, right? If I only consider the linear part of the Einstein's equation, in that case, yes.
Yeah, so this is the part basically the linearized version of the Bianchi identity.
Yes.
Okay, because Bianchi, the full identity was d mu of r mu nu minus half r g mu nu equal to 0. And this is the linearized version of that. But this in turn means that if we now look at the Einstein's equation, okay, these are of course exact Einstein's equation. Okay, this means that for consistency, we must have del mu of t mu nu plus tg mu nu.
Do we know to be del mu of t mu nu to be?
So this one is the usual energy moment conservation that you see in flat space. Okay. And its consequences are exactly what you have in flat space time, namely the total energy is conserved. Okay, as long as the flux of energy is 0, the total energy is conserved. If there is a flux of energy, then total energy can change, but that change is controlled by how much flux is going out. So this is the advantage of using this formalism. Okay, that if you define Pg by this formalism, then you have a notion of total energy conservation. So if gravitational wave has to be produced by some source, the source must lose energy. And imagine that you have some source, okay, which produces gravitational wave. The total energy of the source plus the gravitational wave must be constant. That's what this is saying. Is this clear?
Sir, but does it have to only be like a source having gravitational? This here you have
No, anything. The source produces gravitational field. If the source produces gravitational field, right, the total energy density as a function of time, let's suppose it's a time dependent source, right, which is producing a time dependent gravitational field. So what this is saying is that the total energy density of the source and the gravitational field is constant. Exactly.
So when I have to say I have a dynamical system and I am writing some conservation equations, so I can treat these two parts separately, and the full conservation law will be like the gravity part coming from this part,
exactly,
Eg, plus whatever remaining conventional energy momentum density I have. That is the full conservation.
Exactly. That's right.
So can we put a stronger condition that each part of the T mu itself have to go to 0?
So in general that is not true.
But if for a field which I know producing the mass, this large T mu of the non-gravitational part to be del mu of T mu to be 0.
But that is not true. No? Del mu of T mu is not in general true. It's d mu of T mu equal to 0. That is the energy moment of conservation, right?
Yes.
D mu is not the same as del mu.
No.
So,
And that's precisely the point here. Okay?
Yes.
The point is the d mu T mu equal to 0. Of course, that is true, right? That happened without taking separating out the linear, the part of non-linear part. But d mu T mu equal to 0 does not tell us that the energy density is constant. The total energy is constant, right?
Yes. Yes.
This one, it can be interpreted directly, okay, as the conservation of energy density as you are familiar in flat space. Okay. E mu T mu equal to 0. Okay, that of course also captures the conservation of energy, but not in the usual sense.
So then what is the problem? Say, this is an aside, like in terms of writing, say, field theory, they are interpreting the conserved current in field theory. If I am doing things in a curved background,
Yes.
is this boils down to this simple fact that the conserved current would have this part coming from the field themselves, plus the gravity part is coming only from TG there.
Yes. So this of course is useful only if the gravity part produces a small fluctuation around a flat background. Right? If your background, for example, is not Minkowski, right, but say de Sitter or anti-de Sitter, okay, then it doesn't make sense to think of H as a small quantity.
But you have never used the fact that.
Well, I have never used it, right? But the point is that if G mu differs from eta mu everywhere, right? Then even in the absence of any small fluctuation, this will be non-zero, right? So then it's not very useful. Say a de Sitter space, for example, is static. Okay, that is a coordinate system that you can use, which describes a static universe. But nevertheless, its conservation law is not something that you can say that energy density is conserved. Okay, because it's also expanding. Okay, in some frame, it's also expanding. Okay. So at all times, okay, so it expands at the expense of gravitational energy. Okay, but it's writing it this way is not very useful there. Okay. So it's only if your background is Minkowski. Okay, let's imagine that you have a Minkowski space-time and you have some something happening somewhere in the middle. Okay, asymptotically it's still Minkowski. Then it's useful to write the conservation law this way, okay, and assign separate energy momentum tensor to matter and gravity.
So, but again the same point. Why? Because your whole analysis is independent of the condition that H mu is.
Oh, true. So this equation is true. Right? It's not very useful. Right? Because this equation, right, even in the absence of, suppose you take de Sitter space, right, the expanding universe, no particle anywhere. Okay, even then this is true. Okay, but there thinking of the TG mu is non-zero there, because de Sitter space metric is not eta mu, right? So normally you would think of the definition of TG mu as something that measures what you have created above the vacuum.
Fluctuation.
Exactly, fluctuations about the vacuum. Right? I am not saying that there is anything wrong with this. Right? But it's just that it's not very useful there. So think of it this way.
how in this formalism, sir, you can explain like black holes and all, how you can explain this formalism?
Yeah, so if you take a black hole, right, the total mass of a black hole, suppose the black hole is rotating, right? Okay, doing or rotating or it's doing various things by which it's radiating energy, right? Black hole with some star orbiting around it. Okay. Then what it says, the total mass, okay, or total energy of the black hole plus a star and the gravitational energy radiation that is being produced, that is constant.
No, but
So
what
if-
I'm asking is like time dilation or this stuff like that, like the event horizon which we used to have. We have
Yeah.
a geometric structure where actually the time and all used to like if you have some point near the horizon or something,
Yes.
then the time amount of time for a given detail is very large, like that.
Yeah, so you can always go back to geometric interpretation, right? This is just a rewriting of the same equations.
True,
I have
but
not changed the Einstein's equation to something else.
if I want to use such a relationship, because now you have a somehow you have a flat metric background of your
Exactly, yeah.
right. So now how you can interpret this thing? What is
No, so
happening?
this is useful only if the deviation from flat metric is small. Okay. If the deviation from flat metric is large, then you can split it this way, but then it's not very useful to this relation. Okay. On the other hand, if you have just two ordinary geometric objects, right, not black holes, some stars, okay, which are moving around each other, then it is useful because it's relating how much energy the star is losing, okay, to how much gravitational radiation is being produced. Yes.
Suppose there is a source, there is one part of geometry and somewhere far from it there is another source and it is sending some gravitational wave.
Yes.
Okay. Will there be some added T mu nu for that? I mean, suppose we have some electromagnetic field, we add some T mu nu for that.
Yes.
If there is some gravitational coming from far away,
Yes.
will there be a T mu nu added?
Not in the Einstein's equation. If you use the full Einstein's equation, then nothing, no T mu nu will be added. If you use R mu nu minus half R G mu nu on the left hand side,
This
yes,
one-
here of course yes, you have to add T mu nu.
This one is just giving a source. I mean, you are describing just taking some part from the left hand side and taking it to the right
Exactly,
hand side.
that's
So it is for that. Yeah, only. I mean.
Yeah. So the point is, if you
That-
are using this equation, then this T mu nu will have to contain that if there are two stars and one star is sending a gravitational radiation, the total T mu nu that you have to use around the other star should involve the T mu nu of the star plus the T mu nu of the gravity wave that is coming.
In classical gravity, we generally usually don't consider it as a particle rather than ripples. So does it have an, well-defined energy momentum tensor in that sense?
In classical gravity.
Classical. We consider it as a
No, classical gravity, the point is if there is a gravitational potential, right? You can assign an energy density to it. Okay. But it's just that it's very, very small. So you don't see it normally. Gravity doesn't act as its own source, right? The Newton's law of gravity is linear equation. Right? So you will not see this. This effect will not be seen in the Newtonian approximation. Right? Because Newtonian laws are linear. It is like positive equal to del square phi is equal to source, right? And then that source you do not include the gravitational energy density. So the fact that the gravity can act as its own source, that is the effect of nonlinearity in the Einstein's equation. Is this okay?
So is there any characteristic velocity which
It's the velocity of light because the k square is 0, right?
Mass.
K square equals 0 basically means that k0 and k mod k are the same. So from that you can calculate the velocity. And
There
that
also the wave equation we got, there is also factor of 1 with t,
factor.
because it was just like the light equation, famous.
Yeah, exactly. So the wave equation that we got, right? We have set c equal to 1.
And we got 1.
So that wave equation tells us it's e to the ik dot x, right? And so if you think of this as a wave, you can easily say this propagates to the velocity 1.
this equation talks about the whole space-time we have, right?
So this is a local equation.
Yes.
Right? So this equation is valid locally in space-time.
So there is
This is true everywhere in space-time.
Yes. But what I'm trying to say that if a universe is a collection of several sources,
Yes.
then at every point I can always calculate the contribution of every single source. Right?
Yes.
In that case, this Tg mu nu is the total incoming gravitational wave contribution from all existing sources.
Exactly. Yeah. So because the h mu nu, the Tg mu nu can be expanded in a power series in h, right? Just total h mu nu that you have in the system. Right? It can come from due to gravitational wave from one source or multiple sources. Right? In fact, I mean the way I have written it, I have not even said that it's due to gravitational wave. Right? It's any gravitational field. So will produce a Tg mu nu if you write it in this fashion.
The idea of the gravitational energy density does exist, but without the flat background, the idea of gravitational wave is not quite.
No, even the gravitational energy density, right? It's really useful in flat background, right? Or in maybe some special backgrounds, because this splitting that I did, while you can do it in any background, right?
Yes.
It doesn't really have any significance. Why eta mu nu plus h mu nu? You could have done it by splitting into some other background.
Yes.
So yeah, that
Plus
I
h mu
can
nu. You can
calculate
write
the
similar
different
equation there.
So suppose some different background, then we can put there instead of eta mu nu that.
Exactly, right? But then what happens is this dl mu will be replaced by d mu in that background.
So nothing conservation.
So the conservation idea of conservation law is only clear only we are talking about the flat.
The point is it's clear also in the other situation, right? Even in the general frame, it's d mu t mu nu equal to 0. That's the general conservation law, right? Is there if you want to use your usual intuition of conservation law, right, where the total energy is conserved, right, then this is useful to write it this way. Okay, just because you are familiar more with what you mean by conservation law in flat Minkowski space.
So sir, can't we interpret every problem in relativity, general relativity, as the one which is I am doing everything in as a special relativity, treating everything as eta mu nu, and treating this as also a source, and that is something another gravitational field, just like that.
You can do that, but it's not, as I said, it's not very useful often, right? Because if the energy density is pervading the whole of space time, right, then what are you conserving? Because the energy flux never vanishes, right? Because this conservation law is useful if you assume that asymptotically there is some place where the fields go to 0, right? And then the total energy density is conserved in the intermediate state, right?
So for every case where my asymptotically I am flat metric,
Yes, there you can use these formulas.
so there I can just remove all the geometric interpretation and treat this as a field.
No, you can remove the geometric interpretation any time, right? By making an arbitrary splitting. But the fact that you are using this, you are writing the equations in a way where you have removed the geometric interpretation doesn't mean that the geometric interpretation has gone away. It's the same theory after all, right? The same set of differential equations you are solving. It's just that yes, for some things you don't need to look at the geometric interpretation. It's more useful to think of it this way. For something else, it's more useful to use the geometric interpretation. And these are the different tools for studying the system under different circumstances.
So, this Tg mu nu for every background it's very close to the Minkowski space. If you write it like this, it will always give positive contributions to the tuning.
Yes, it turns out that it gives positive contribution, but that requires some theorem. That is not easy to prove. That, but eventually one can show that there is this positive mass theorem.
That requires small h mu nu or for any h mu nu, it will always.
The point if it's asymptotically flat, right, then what we can show is that the total energy density contained in any region is always positive. Yeah, that's the positive mass potential. I mean, you cannot, of course, locally you may not say that if whether it's positive or negative. Okay, but globally, right, one can show that the total energy or the total mass contained in a given volume, in fact, Minkowski space, is always positive. Provided the matter energy momentum tensor satisfies some appropriate restriction. because you cannot decouple these two completely, because the equations of motion couple them. Okay, T mu nu determines T G mu nu and vice versa. But what one can show is that by once you impose certain condition on the matter energy moment of tensor, then the total energy contained in a given volume is positive. Okay, so far we have discussed this gravitational wave. Okay, but now one can ask also how do you produce gravitational wave. Okay, so I will not discuss this in great detail, but the point is they are produced exactly in the same way as you produce electromagnetic wave. Okay, because basically you have the Einstein's equation with sources, right? You can think of it this way or in the original Einstein's equation. On the right hand side there is a source, right, which is the ordinary matter moving around, and we can then calculate the field, gravitational field produced by this source using the standard Green's function technique. Okay, if you ignore the nonlinear terms, then it's straightforward the standard Green's function technique. If you take into account nonlinear terms, then we have to add corrections. Okay, but those corrections are very small typically. Okay, so you can use linear equations to determine what kind of gravity wave is produced by a source term. Okay. But in that process, okay, we have this conservation law. Okay. And this in fact is one of the only experimental test of gravity wave. So let me describe that. So this involves what is called the binary pulsar. Okay. So the binary pulsar essentially is a system of two stars which are orbiting around each other, two close by stars which are orbiting around each other, and one of them emits electromagnetic wave for some internal process, okay, which you don't worry, okay, but it continuously emits electromagnetic wave. Now, we of course don't see these two stars, okay, because they are typically very far away. But what one observes for a binary pulsar, the way one recognizes a binary pulsar is that the frequency, suppose this is the star that emits electromagnetic wave. The frequency of this electromagnetic wave has a periodic variation, or no, I should say frequency of this electromagnetic wave. Okay. So basically, what happens is a pulsar, okay, keeps sending pulses. Okay, we are not worried about the frequency of the pulse, but it just keeps sending pulses at regular intervals. Okay. Now, the interval at which it sends the pulses, okay, that turns out to a periodic variation. Okay. And that periodic variation is assigned to Doppler effect. Okay. If, for example, these two things are moving around each other, and suppose you have a source here, okay, then when this star is approaching you, okay, it will look like that the frequency is higher, right? And when it's going away from you, okay, then it will look like the frequency is lower. Okay. So this periodic variation of the frequency at which the pulse is coming, okay, that's what is used to recognize that this is a binary pulsar. Is this clear?
So the frequency of the pulse.
No, frequency of the pulse, not the electromagnetic wave frequency.
That will be neglected.
Yeah, that is some number, but this is that it pulses, which means that it gives out these electromagnetic waves at regular intervals. Okay. That interval, okay, varies for a binary pulsar, okay, because as the pulsar is coming towards you, okay, it looks like that the frequency is higher. At the pulse is going away from you, it looks like the frequency is lower just because of the Doppler effect. Is this clear? So this is a binary pulsar. But then what one finds is that if one observes this for over a long period, okay, at least some binary concept, that if you observe it over a long period, then this period over which it varies, okay, the period over which it varies is the orbital period, okay, because when it comes towards you versus when it goes away from you, right, that's the period, okay, that's the orbital period. What one finds that this orbital period, okay, reduces over time. Is this clear? And this reduction means that this distance between these two objects is reducing with time. Right? In other words, this is losing energy. This system is losing energy. And that loss of energy one can assign to emission of gravity wave. Okay, that the energy is being lost from this orbit, from this binary pulsar, because it's, as it rotates, okay, it acts as a source of gravity wave and it emits gravity wave. Okay. Now, how much gravity wave it emits can be calculated by the Green's function method, right? Because it's a known source, right? It's just two objects revolving around each other. Okay. Using that as a source, you can use the standard Green's function technique to calculate how much gravity wave will be emitted. Just like if you have an oscillating charge particle, right? If you have a moving, say, suppose you have a charge, positive charge and negative charge orbiting around each other, you can calculate how much electromagnetic wave it will emit by Green's function. It's the same story here. You can calculate how much gravity wave will be emitted. Based on that calculation, you can also calculate how much energy it will lose. Okay. And that prediction can be compared with the rate at which these objects are coming close. Yes.
This energy loss is over and above the electromagnetic loss.
The point is, these are not typically charged particles, right? So there is no electromagnetic wave.
But the pulses that you are seeing,
That is due to
what
intensity.
Yes. So that electromagnetic wave loss is actually negligible here. You are saying that just because the electromagnetic energy is coming out, right? It's losing some energy, but that's negligible. When these objects are very close to each other, okay, then the energy loss due to gravity is much more.
So the difference, the change in the rotation period or whatever is accounted in most parts by the
Mostly by the gravity.
Gravity.
Exactly.
If somehow this distance is such that they are between the rho plus and rho minus that we saw, is this orbit is static somehow
Between rho plus and rho minus.
so when you calculate the different motions under gravity,
Yes. See, there it was elliptic orbit actually, right?
yes,
Elliptic orbit and then there is rho plus and rho minus. Here you can think of it as circular orbit. To ignore the eccentricity, then it's a circular orbit. Okay. So the distance would have remained fixed if there was no emission of gravity wave. See, even in that case, right, if you go through the analysis completely, there you use the fact that it's like a test particle moving in a given background, right? But the full set of equations will be the coupled set of equations involving matter and gravity, right? So once you take that into account, right, you will find that again, even in that case, the orbit loses energy. Because you solve, see, when you got this orbit, right, we got an elliptic orbit, okay, which is, we saw this perihelion precision, right, but you could also consider circular orbit in principle. Okay. But in that analysis, okay, we didn't take into account uncertainty, right. That analysis was purely based on thinking of this as a point particle moving around a given background. Okay. The fact that the metric itself could change with time, that you hadn't taken into account. Okay. Once you take into account the full coupled equation of the matter and metric, okay, then you will find that the orbit actually is not circular. Even if you start the circular orbit, it slowly spirals down. Okay, particularly if they are too close, very close to each other, then the rate of spiraling becomes large. Okay, because it's rotating very fast, right? And that means that the rate of emission of gravity wave is also sufficiently large. Okay, and it keeps losing energy. And that loss of energy you can calculate.
So just like electromagnetic case.
Yeah, just like electromagnetic case, if there is a particle, if there is a plus minus charge revolving around each other, you can calculate how much energy it will radiate. Okay? It's a similar calculation here. The equations are different, of course, okay, but the technique is the same. So then you can compare this with the So you use the energy momentum conservation. Once you know how much gravity wave is produced, right, you can use this equation del mu of T mu nu plus Tg mu nu equal to 0. So if you are producing certain gravity wave which carries a certain amount of Tg mu nu, it must be compensated by a change in T mu nu. Right? And the T mu nu change, that is the gravitational potential energy that is being reduced. Okay, so they are coming closer to each other. Okay. So this calculation can be used to predict at what rate these orbits will come close to each other, at what rate the period will change. Okay, that you can compare with the experimental observation and you get a perfect agreement between what theory predicts and what experiments give. Okay, so this in fact is the only direct experimental or indirect experimental test of gravity waves that you have. Is this yeah? Okay. There are also of course direct experimental the experimental setup which tries to directly test the existence of gravity wave. Okay, so maybe I'll say a few words about that and then I'll stop. So direct experiments So direct experiment essentially uses this fact that E11 is equal to minus E22 for a gravity wave. Right? So if the gravity wave is propagating in the third direction, then E11 and E22 are opposite. Now E11, okay, that means H11 is equal to minus H22. But H is just a term that is added to the metric, the tweeter. Okay. So if for example H11 is positive, that means that G11, which is eta 11 plus H11, this is greater than 0 or H11 greater than 0, and G22, which is eta 22 plus H22, this is now less than, sorry, this is greater than 1, this is less than 1 for H11 greater than 0. Okay, because H22 is minus H11. So if we have say some fixed points in space, and if a gravity wave passes through this, what will happen is that periodically this distance will shrink, this distance will increase, and vice versa. Right? So as gravity wave passes, H11 of course oscillates. Right? So it's positive in some place, sometime negative in some other time. Right? Because H11 oscillates. So the oscillation is such that when this shrinks, this expands, and when this shrinks, this expands. And that's the kind of oscillation you expect to see. And this in principle can be detected by interference experiment. Okay? If you use interference, okay, where you adjust your apparatus so that there is zero signal, that imagine that there is light which travels along this length and there is light which travels along this length, and then you make them interfere. And assume that you have set up the apparatus in such a way that there is destructive interference when these distances are exact. You will see a signal. Okay? Because during the passage of a gravity wave, this distance will shrink, this will increase, and vice versa. And that's what we try to detect. So far there has been no signal of gravity wave that has been detected this way. Okay, but this is a big experimental setup that exists. Okay, and in fact it spans several countries, and now India is also going to join one part of the experiment.
So in this case, already the metric is Schwarzschild metric.
Well, the point is because of we are on the Earth, but that effect is small, and you can correct for that. Okay. Right? In fact, you have to correct for the effect of Earth's gravity, also the local disturbances, right?
Sun's gravity.
Whatever, I mean, you have to calculate everything. In fact, local mountains, for example, will distort, right? So all of those you can in principle have to calculate and correct for. But the point is that because this is an interference experiment, those local disturbances typically are static, they don't change. Right? So suppose you have set up your experimental apparatus so that you have destructive interference, exact destructive interference, right? That's the time independent configuration. And now we look for signals when the gravity wave passes through it. Okay? So the main cause of errors in these experiments, right, is not the presence of static sources, right, because those are of course you can correct, okay, but just local vibrations, for example, right? I mean, those can send wrong signals, right? If this distance, for example, changes not because of gravity wave but for some local vibration, okay, then you will apparently see a signal which is not due to gravity wave. Right? And those are the things you have to correct for. So this is called LIGO. Okay, and as I said, this is also an experiment. Now India is planning to join.
Sir, up till now there hasn't been any source like registered for kind of.
No, not direct experiment. There has been no gravity wave prediction.
So in this binary
But as I said, the binary pulsar is a very good indirect test for the existence of gravity waves.
This part has been tested.
Yeah, this has been tested. So the binary pulsar, yeah, people have actually calculated the rate at which the orbits will come close, and you compare the experiment and you get perfect agreement. So this has been tested, and so that's why you know already that experimentally gravity waves must exist.
What is the time period that they have watched? The time.
I think a few years, if I remember correctly, but there are different pulsars with different periods.
One star is usually a neutron star.
That's right, which is emitting the pulse.
Does the smallness of h mu allows us to set up an apparatus such that will be significant to observe? I mean, so it will be such that the 4 points that will
Yes.
be very small that we cannot set up an apparatus.
Yeah, so the point is that that's the reason why you want to make this point very, very far away.
That
The point is, the h mu of course is small, right? But you see that this factor multiplies the metric, right? So total distance by that changes is the original distance L multiplied by this factor, right? So even if h11 is small, right, the change of length can be made large, right? Because it's L times this. Okay, that's why typically gravity wave experiments are very, very big to just enhance the interference effect.
Because the signal is very
Yeah, because the signal is very small. Yeah, typically H11 is very small. Yeah, but you try to enhance the effect by simply multiplying by long length.
So, but checking such a thing is just a recheck of Einstein's gravity.
Yes, complete, I agree. Right? That's why nobody doubts that this exists. Right? Because Einstein's gravity has been tested in many different ways.
And this also gives some
This also is a kind of a check of Einstein's gravity.
Exactly. This is also kind of check of Einstein's gravity. Right? But one of the reasons for gravity wave experiment is that people believe that once the experiment becomes sensitive enough, right, we can see parts of the universe using gravity waves that is not probably visible in electromagnetic wave. That there may be things going on in the universe which do not emit any electromagnetic wave. Right?
Like
So,
in dark matter and stuff like that.
for example, right, dark matter, even ordinary matter, right, which is
Of
non-luminous,
course. Yeah, no.
right, which are not visible to us, but nevertheless they emit gravity waves, right, and those could be visible, and you may learn a lot more about the universe than you know from the visible spectrum or the electromagnetic spectrum. But that of course will first require us to detect gravity wave from something, right, and only then we can use it to study the universe.